Hello everyone, my name is Brian Crutchley. I'm a student at the Department of Computer Science, Mathematics, and Engineering at Shepherd University. This is my project software developed to facilitate calibration of tumor growth models. Here's the abstract. Impulsive ODEs can be used to model complex real-world behaviors such as tumor growth and provide insights into how therapies work. Additionally, these models can be enhanced through complementary software that is able to better manipulate the large sample spaces their parameters tend to have. This project seeks to develop a series of software to numerically solve multiple newly developed tumor models and facilitate the simulation of model calibrations against experimental data. The impulsive ODE solver is accomplished by using the Runge-Kutta method to approximate solutions to the models and leveraging computational power to achieve high precision and speed. This series of software help with data input, output transfer, speedy pick of optimal calibrations, and graphing in the simulation of a couple tumor models. A little on the model. It was originally introduced in numerical simulation of a tumor growth dynamics model using particle swarm optimization by Zheng Wang and Qin Wang. A paper built tumor cell growth models, which usually involved coupled differential equations with a high dimensional parameter space. This project followed in its steps and built a similar numerical solver for a model created by another member of the research group at Shepherd. Along with the software, various software was built to facilitate managing the data generated. Here is data flow within the software system. There are three main stages. It's data gathering, data pre-processing, and then data analysis. Here's some of the technologies that were used. C# is the programming language that was used for all software. It's developed by Microsoft. Closed XML software library in C#, which allows interfacing with Microsoft Excel files. Then R, the statistical programming languages, which was used for generating the more complex plots. Stage 1 had one main software, which was the simulator. Its main goal was to exploit a parameter input space to find the set of parameters that fit real-world data supplied. And its simplified logic is as follows. Taking the parameters and impulses, the parameters are used for controlling the tumor state, and the impulses are used to represent treatment methods against tumors. Simulate the tumor growth. Test against provided real-world tumor growth data, and then adjust parameters to get closer to the real-world tumor growth data. In actuality, this is done multiple times across multiple different inputs, and so it ends up generating a massive amount of data. That's where the data pre-processing stage comes into play. The main software here is the importer, which transforms the data outputted by the simulator into a form that is more convenient to use. The simplified logic here is taking text files generated by the solver, split them by line, split the lines by spaces and tabs, and then insert each word generated into an Excel cell. What this does is it packages all of the text files into a handful of Excel files with a bunch of sheets in them. And then we can process these in our later stage. In the data analysis stage, we process those files with three main programs. The first one is 3 curves, which generates a 90% upper confidence curve, 90% lower confidence curve, and a meaning curve from a group of tumor growth data. And so what this lets us analyze a batch of files and see how close that whole group is to real-world data. And this sort of lets us see if we're getting closer to the real-world data and fitting our parameters, because the search space is so large. It helps to have that visualization. The next program is violin plots, which generate violin plots to demonstrate the sensitivity of the various parameters. And this lets us visualize this and then look at the charts and say, for this group, we need to increase the values of a certain parameter. And that way it'll influence the overall trend towards a certain real world data point. The best fit finder and best fit ranges is the last program. Its goal is to extract the best fitting results from a group of results based on how close it is to the real world data. And this usage essentially you take the outputs, score the results relative to all other results, and then rank them. And then we take the top end ranked results depending on how large we want the next data set to be. And this lets us sort of look at a very large set of data, trim out all the useless results that didn't fit well at all, then have a set of sort of actually good data that we can then use to run the training again and get closer to fitting towards the real world data in multiple results. And so here's a summary of the results. We created a suite of software to model tumor growth data and optimize the fitting of the model to real world data. And this suite of software ended up working well. It accomplishes the goal. And it takes a very long time to train, so results are currently inconclusive on fitting a model to real world data. But it is undergoing training and it is getting there. Thank you for listening.